Hey everybody, Corey and Victoria here. We are the Professors DuBois, and in this video lecture we're going to talk about the electromagnetic spectrum, and more specifically we're going to get into wavelength and frequency of light.
Okay, so in general chemistry, this next portion of general chemistry that we're going to be working through is finding the structure of an atom. And after that, once we determine the structure of an atom, we'll move on to the structure and the shape of molecules. So that's kind of where we're going. But we want to kind of step back and remind you that chemists will, and scientists in general, will determine information about the atomic scale by making observations on the macro scale. So we're bringing this back, we're doing this again, and specifically we're going to be talking about how does matter behave when we input energy. So we add energy, maybe it's in the form of heat or some other form of energy, and then how does that matter behave? And oftentimes we'll see that atoms will absorb that energy and then emit it as light. And this light tells us about the structure of the atom. But before we get to the structure, we're going to be just talking about light.
Sorry, I jumped ahead there. I just had my finger on the
You're
arrow.
so excited.
Yeah, so we're going to just study light a little bit, and this seems a little bit out of character, but you'll see very quickly how this is very important to understanding the structure of the atom. So let's just focus on light and what is light. We actually have an entire spectrum of light. Now we're used to, when we say the word light, we're used to talking about the visible spectrum, which is actually a very, very small piece of the entire spectrum. And so we can call everything in this spectrum, we can call it light, or we could call it electromagnetic radiation. It's called the electromagnetic spectrum. So you'll notice here we've got some terms for these different regions. We've got gamma rays and X-rays on the left, and we've got on the far right, we've got microwaves and radio waves. And you can see up above it, it appears to be waves, kind of drawn like a squiggly line. We'll get into this a little bit more. We've got this term frequency that has units of seconds to the -1. That's the same as 1/seconds. So we're going to have to talk about frequency. And we also have wavelength here. So this is units of meters, and these are all things to consider when we're looking at a wavelength of light, or a wavelength from the electromagnetic spectrum.
All right, so let's kind of dive into these waves and dissect them into their parts. So we have amplitude, which is the distance from kind of the baseline to the top of the wave or the bottom of the wave. It's the same here, and we're showing two waves that have the same amplitude, but they're very different, and they're different parts of the electromagnetic spectrum. And if we measure from the peak of one wave to the peak of the other wave, that literal distance is the wavelength. And you can see on the top we have a picture of a longer wavelength than a shorter wavelength on the bottom. And we also have something called frequency. So if you have these waves, if you picture these waves traveling forward and going past this barrier, say, they travel at the same speed, which we're going to talk about in a second. So if they're traveling at the same speed, we would have more waves pass by the barrier in the same amount of time, and that's frequency.
I like to think of frequency as like waves per second, because the units are per second, 1/seconds, and that kind of helps me. So if we had a snapshot in time, how many waves went by in 1 second, that would be a frequency unit.
Yeah.
So you can see that longer wavelengths would have lower frequencies because they are traveling at the same speed. So you can see this higher frequency has the shorter wavelength, so more waves will end up going by in a given amount of time.
So light is an electromagnetic wave, and that entire spectrum is the electromagnetic spectrum. So X-rays are light, and microwaves are light, and they all travel at the same speed, which is this 2.998 times 10 to the -8. You probably have seen this in high school as 3 times 10 to the 8th, but since we are concerned with significant figures, we want to make sure that we don't truncate our significant figures based on the number that we use for the speed of light in our calculations. So get used to using this, and any wave on the electromagnetic spectrum can be characterized by its wavelength and its frequency. So if we know its wavelength or its frequency, we know where on that spectrum we are. Wavelength, we designate that with a lambda, and the typical units are in nanometers, but it's really, meters, right? So it's a distance, it's a length. And frequency it's typically in hertz, and you'll see it as hertz like this, or in reciprocal seconds. So it's kind of like a count, right? A count per second, and you might see it 1 over seconds. These are all the same thing.
So that speed of light, that is, when that is measured, that's in a vacuum. And what's meant by in a vacuum is there's nothing present, there's no air present, so there's no interaction. So that value is based on light that is not interacting with any other material, just traveling through empty space.
All right.
This is the relationship between the speed of light and the frequency and wavelength of a wave. So notice how our units are very important here. Our frequency has units of hertz, or 1 over seconds, and our wavelength will have to be in meters to use this equation. So something to watch out for is just unit conversions. It is very common to see wavelengths in nanometers. So if we're going to apply this equation, we have to convert from nanometers to meters. So just watch those units. Speed of light's always given. It's always going to be available for you. So if we have a frequency or a wavelength, we can calculate the other using this relationship.
So here's an example. What's the frequency? So we're looking for mu. The frequency of light with a wavelength of this, and it's in meters. So we can use our formula. We'll go forward 1 and show that. Did
we mention that before, that the symbol for the frequency was that nu symbol?
I don't think so.
So it looks like a lowercase v kind of. It's just
italics.
Yeah.
Yeah.
So that's the frequency, and the lambda symbol is our wavelength. You did mention that.
Yep. So we have our speed of light, which is c, and our wavelength is in meters, so we can use it directly and solve for the frequency. So I could have also called this hertz. I could have also represented it as 1 over seconds, or reciprocal seconds to the -1. So they all mean the same thing, and you'll see them interchangeably used.
So that was pretty straightforward because the wavelength was given in meters. In this example, we have, probably more common, they want to know the frequency of light with a wavelength at 400 nanometers. So the first step is going to be converting from nanometers to meters. We have your conversion factor here. You'll want to be able to do this. There's a lot of this type of conversion in this chapter.
For sure. So the blue gives you your conversion from nanometers to meters. So your nanometers cancel. And we have 3 significant figures, so we're going to retain those 3. And then we use our formula for the speed of light and solve again for frequency. Now you could have been given the frequency and solve for the wavelength as well. And if you do that, anytime you solve for the wavelength, that will be in meters. You might have to then convert it to something else after that.
All right, so here's a practice problem for you, and we are looking at the frequency of blue light, so we've even got a color associated with this. Given the wavelength 435, is that in the blue range?
I hope so.
I hope so too. Might want to check that. So, regardless,
put a note in the comments if it's no.
It's a good question to work through. So,
pause the video and give it a try.
So here's your answer. Do you want to walk through this, set up the formula, or?
If you'd like. We have 435 nanometers. First, we have to put that into meters because we want to be able to use our formula. This is 4.35 times 10 to the minus 7th.
Meters.
And meters, thank you. So our speed of light is 2.998 times 10 to the 8th meters per second equals our wavelength times our frequency. And we can solve for frequency and we'll get that.
All right. Thanks for watching.
Appreciate you tuning in. Come on back for more discussion of light and how that will then lead to our structure of the atom. Have a good day.